And so in the previous episode, we were looking at this idea of molecular shapes, how the atoms arrange themselves in a compound, so the actual physical shape that molecules have, and how that related to this idea known as VSEPR theory, or valence shell electron pair repulsions. In other words, in lay terms, electrons repel one another. In repelling one another, they're going to try to get as far apart from one another as possible, and in doing so, they will then produce very distinctive shapes. And so below, what you'll see is that I have the 5 major types of molecular geometries. Now, I'm going to speak into this a little bit, but what I want you to notice first and foremost is that we've already spoken about 3 of these. We first had over here on the left, we had our linear shape. So if you recall, this was basically something like carbon dioxide. You had the carbon in the middle, and it would basically throw some electrons to the left, and it threw some electrons to the right. In essence, creating, as we spoke about earlier, this nice little straight line between the two of them. Now, why is the linear shape, of course, going to be one of the simplest? Well, because again, in this shape, we have an angle of 180 degrees. This gives me maximum distance between my electron clouds. Then from there, we looked at something like sulfur trioxide, and we said that when we looked at something like sulfur trioxide, again, this would have been my central sulfur, and we see that it would still be two-dimensional because in essence, what it's forming is simply going to be a triangle. Now, what I want you to notice is that above each of these molecular geometries, let me rephrase it, on top of each of these molecular shapes, what you'll notice is that there is this number. So electron groups, 2, 3, 4, 5, 6, etc., etc., etc. So I'm not going to refer to these as electron groups. Instead, I'm often going to refer to these as possible bonding sites. And what I mean by that is where could, notice the emphasis on could, where could another atom hook up? So for example, if I come back over here to my linear and we go back to something like carbon dioxide, in the case of carbon dioxide, the carbon threw its electrons to the left and to the right, meaning that in theory, something could come over here and latch onto this side of the carbon, and just as likely something could have come over here and latched onto this side of the carbon. Does that mean that necessarily just because you have electrons there, something must hook up there? No, not necessarily. That's why I referred to it as possible bonding sites. But it is important to note that depending on the number of electron groups or depending on the number of possible bonding sites, that is going to influence how the electrons will be oriented. Or another way of saying this is going to be, instead of the molecular geometry, we can refer to this as my electron geometry. How the electrons are going to be spread apart away from one another. And so what we notice, as we said earlier, is that each of these is going to have its own distinctive, unique shape. So we had, of course, the line, linear. We had our trigonal planar. We had our tetrahedral, right? And so then, after tetrahedral, we get to this idea of 5 possible bonding sites, or what happens in the case of an expanded valence shell, where you now have electrons going off in 5 distinctive directions. And we refer to this as a trigonal bipyramid or a trigonal bipyramidal. Depending on which text you're using, you'll see it, again, tomato, tomato. And after we have 5 possible bonding sites or 5 electron groups, you're then going to see here at the end, we have our 6 possible bonding sites. And these 6 possible bonding sites, again, this is going to more than likely occur when we have an expanded valence shell, but this is known as an octahedral. Okay, now, why are all of these electron geometries important? Because the entire time, what the electrons, as we said earlier, they're trying to do is get as far apart from one another as possible. And so these are going to be important because, for example, if I were to look at something that we knew was going to have 5 possible bonding sites, for example, if we looked at phosphorus pentafluoride, when I draw my Lewis dot, I would draw my Lewis dot something like this. I would go, okay, so we're going to have a fluorine and a fluorine and a fluorine and a fluorine and a fluorine, right? And of course, each one of these fluorines would be filled. You get the idea. But again, let's focus for right now. Let's focus on that central atom. Because if I look at this, I may very well lose my mind and think for a moment that I have a flat molecule. Couldn't be further from the truth. Instead, what we want to notice is that when I have 5 possible bonding sites, we actually have this configuration here. This trigonal bipyramid, or this trigonal bipyramidal, is what it's going to actually look like. So what I may want to do to help my little brain try to process all of this is that when I draw that same phosphorus pentafluoride, what I might do is I might actually draw almost a little triangle here in the middle. I'm going to put my phosphorus here, and then I'm going to go ahead and send one up, and I'm going to send one down. And the reason I might do this even on my Lewis dot is that, so again, I recall that it's going to be a 3-dimensional shape. Now, do you have to do this? Of course not. We can easily get rid of our triangle. That's not a problem. But what you should notice is that by doing it in this fashion, again, it might give me pause. So I go, wait, this is a 3-dimensional shape. Again, what's the significance of it? Well, in this 3-dimensional shape, yes, we still have a 90-degree angle. So there's 90 degrees there, no different than if I look over here. This is a 90-degree angle between the top and the bottom. But if you look closely, it seems like in the middle of this structure, I actually have a triangle, which means that this angle here is going to be 120 degrees. Now, does that mean that every single angle on the trigonal bipyramid is the same? And the answer is no. But because I have 120 and 90, that's better than if I put everything on a 90-degree angle. And so this is why the trigonal bipyramid is going to be the shape that our molecules take when there are 5 possible bonding sites, where there's 5 places that these things can attach. And last but not least, we have what happens when we have 6 possible bonding sites. This is known as our octahedral. Now in this case, now we're really slapping all of these electron clouds as close to one another as they can get. And so unfortunately, at this point, there is no other option. Everything is now going to be 90 degrees. So we're going to have 90 degrees from this angle up here to this one there, the same way like there's going to be 90 degrees on that central square. There's just no 2 ways around it. But I did not get to a structure where everything was 90 degrees until I had 6 possible bonding sites, or 6 electron groups. That's pretty good, because remember, we're not going to get to something like an octahedral until we have a very large expanded valence shell. So octahedrals are going to be structures that we're not going to encounter that often. They should be few and far between. Now, depending on your level of chemistry, there is one more structure which I am not going to attempt to draw because you've already seen my artistic ability. But for the most part, these 5 that we have in front of you are going to be the most common electron geometries that you must know and know how to draw. So again, we have the linear, trigonal, planar, and tetrahedral. Typically, again, not always, but typically, these 3 are going to be reserved for when the octet is followed. So if the octet rule is being followed, typically it's going to be some type of linear, trigonal, planar, or tetrahedral configuration. Now, it is possible that you may have an expanded valence shell that still is trigonal planar, as in the case of sulfur trioxide like we saw earlier. But for the most part, cheap and dirty, Those are going to be if the octet is followed. Now, what happens if you break the octet? Well, if you're going to have an expanded valence shell, more than likely, if not almost 100% of the time, in order to have that expanded valence, you're going to need to look at one of these two structures, trigonal bipyramid and octahedral. Again, not always, but the minute I see 5 or 6 possible bonding sites, if I see a structure, I'm like, how am I going to fit that many electrons on that central atom? If you start going down that path and you're thinking expanded valence, then chances are you're going to be using trigonal bipyramid or octahedral. And so, just to kind of see it all from a different perspective, what we spoke about then in this episode was this idea of how can my electron clouds get as far apart from one another to maximize the distance or the angles between them. And so just to recap it, what we saw was that when we looked at our linear structure, we had this 180 degrees. In the trigonal planar, we saw 120. Now, what we're going to be moving towards, and we'll be speaking about shortly, is that what happens if I look over here and we start to notice that instead of having a bond, and a bond like we had on the left, what happens when now we only have these bonds here and we notice that a lone pair now exists up top here. And so this is going to cause extra repulsion. Now, we're not going to deal with it in this episode. This is something that we're going to see further down the line. But what you should notice is that when you have lone pairs, it seems like this angle here gets pinched. So if typically the angle should be 120, when lone pairs are present, we now see it at less than 120, maybe 118, 117, etc., etc. When we had 4 possible bonding sites or 4 electron groups, we had our tetrahedral. This again was about 109.5 degrees, right? But what you should notice is again over here on the right, if we have a lone pair, suddenly now that angle gets slightly pinched. It's now going to come in at 109, slightly less than 109, about 107. Okay, if we looked at, again, 5 possible bonding sites. What you'll see, again, we had our triangle in the middle. So here was our triangle. The distance between all of these clouds was going to be 120 degrees. But between the triangular plane and the one that went up top, that was 90 degrees. Therefore, there were 2 angles in our trigonal bipyramid. Finally, the last one that we looked at was our octahedral. And again, in our octahedral, now at this point, there's literally no place left to go. Now we're going to notice that we have our square here. And that means that each and every single one of these is going to be 90 degrees from one another. And then, of course, we have 90 degrees up and 90 degrees down. And so these are the shapes that our electron clouds can take. Now, all of these that I just spoke into, and we had them earlier up here, so all of these were our electron geometries, how the electrons oriented themselves, to maximize the distance between them. What we're going to see is that when it comes time to see the actual molecular structure or the molecular shape, what we're going to now take into account is where did another atom hook up? Because here's the thing, electrons move really fast. They move so fast that you're not going to see them under a microscope. And so wherever there's a lone pair of electrons, we're not going to really see that. So we're going to be left with some type of different shape. And that's where we'll pick up in our next episode. So we take it one step at a time, one tick at a talk, and you'll be there in virtually no time.